All right, so I guess we'll go through the algebra. It's not, like I said, critical that you follow every step. If you want to, I guess you can fast forward some number of minutes to get to the punchline, but I think it's useful that you see this as a graduate level mechanical engineer. So what are we going to do? We're going to start by taking these two energy balances, and we're going to solve for the outlet temperature. So here I'm solving the hot for the hot outlet temperature, right? And it's just THN minus Q dot over C dot H, right? And then this is for the cold outlet temperature, so TC out plus TC in plus Q dot over C dot C. So this is just energy balance. And then I'm going to express the Q dot here in terms of effectiveness, right? So Q dot is equal to the effectiveness times C dot min times THN minus TCN. And the same thing here. So this is what I'm going to use to substitute into my my solution for the outlet temperatures. So these are my two equations for the outlet temperatures. This is the counterflow heat exchanger solution. So I'm going to take this equation here and put it here for TC out. I'm going to take this equation here and put it here for TH out. And that gives me this equation here. If you look at this equation for a second, you'll see that I have on the top and the bottom THN minus TCN, right? So here's THN minus TCN, here's THN minus TCN, the same thing here. So if I pull that THN minus TCN out of the top and the bottom, which I did here, I can cancel it out. And I'm left with this equation here, which is starting to look a little bit more promising in terms of being in terms of effectiveness. It's already in terms of effectiveness. It's really close to being in terms of NTU and capacitance ratio as well. At this point, in order to proceed, I have to assume that either C dot C or C dot H is the minimum capacitance ratio, the minimum capacitance rate. If you assume one thing and go through and get a solution, and then you go back and you assume the other thing, you'll go through, and if you did that, you'd find you get the same solution. So it doesn't matter what you assume, but it just makes it easier to think about if you assume one or the other. So what I did here is I assumed that the minimum capacitance ratio fluid was the cold fluid, and that means that the maximum capacitance rate fluid has to be the hot fluid. So every place I have a C dot C inside of here, I can put in C dot min, which is what I did. Every place I have a C dot H inside of here, I can put C dot max, which is what I did. And now I'm really in business, right? Because this is a 1. Let's see, this C dot min over C dot max, that's the capacitance ratio. And then over here, if I pull out C dot min, I have UA over C dot min, which is NTU, and then I have C dot min over C dot max, which is a capacitance ratio. So I'm pretty much done at that point, right? This is my relationship between those three-dimensional variables. This is a relationship between the effectiveness, the capacitance ratio, and NTU. This is a relationship that is only valid for a counterflow heat exchanger, right? If I did the same thing for a parallel flow heat exchanger, I'd be able to get a relationship between these variables, but it wouldn't be this one. It'd be a different algebraic relationship, right? That's why there's a different one listed for every configuration. All right, so this is progress for sure. The last thing that makes this super useful is I can solve this for effectiveness NTU, or I can solve this for NTU. I'm sorry, I can solve this for the effectiveness, or I can solve this for the number of transfer units. And those two solutions are useful for different kinds of problems, right? So if you think about a simulation kind of a problem, that's a problem where you have a heat exchanger, right? You know it's UA, you know how you want to operate it, right? So you know the capacitance of the two streams, you can calculate the NTU, you can calculate the capacitance ratio, and what you want to understand then is how is this heat exchanger going to perform? So you want to simulate that heat exchanger. So in that situation, it's a natural thing to calculate the NTU and the capacitance ratio, and then use this to calculate the effectiveness. So that's where you would use that kind of a solution. On the other hand, if I solve this for NTU, that's a useful solution for a design type of a problem. So if you think of a design type of a problem, that's a case where you know the job you want your heat exchanger to do. You know everything about the flow rates, and you also know the performance you need your heat exchanger to have, right? So that means you know the effectiveness. So that's a case where it's very natural for you to calculate the effectiveness and the capacitance ratio. And what you want to do then is use these solutions to figure out NTU, from which you can get the UA, right? So you'll be using either one or the other of these two forms of this algebraic solution. So one thing that I hope you obviously won't be doing is using both of these equations, right? Because these are the same equations. This is the same equation, just solved differently. So if you're writing an ease code and you find yourself putting this equation in and then also putting this equation in, you just put in the same equation twice, right? You'll get garbage probably, and most of the time ease isn't smart enough to tell you you have redundant equations. It'll just literally give you garbage, right? So you have to know, when you're using the solution, and then only use it one time. Okay. So going back to these equations, to these tables, hopefully they make a lot of sense now, right? This is the entry that we just determined. This is a counterflow heat exchanger, and this is effectiveness as a function of NTU. So this is the form of the solution that would be really useful for a simulation type of a problem. If I have different configurations, these equations are different, but they're all expressed in the same way. And then over here, here's the entry for counterflow heat exchanger, but now I have the solution in terms of NTU equals something, right? So now this is a solution that would be really useful for a design type of a problem. And again, if I have a different configuration, I have different solutions, but they all kind of look the same in the sense that they're all NTU as a function of capacitance ratio and effectiveness. Let's see if I can go to ease here. So if we go to ease, we go to options, function information, heat exchange, heat transfer, go to heat exchangers. What you should find here is underneath heat exchangers, you have all these solutions, right? So here's NTU and effectiveness. So what do we have here? We have this first one are these solutions in the sense of I'll give you the NTU and the function will give you back effectiveness, right? So if I click on this, we can scroll through all these different configurations, right? The second one here, or the third one, I guess, is now you give me the effectiveness and the function will give you back NTU, right? So this is more of a design type of a situation. And again, you just scroll to whichever configuration you're interested in, and then you call the function, right? So everything that is found here, plus actually more, is also programmed in those functions in ease. All right, so that's what the effectiveness NTU solutions are. Hopefully you understand pretty well now where they came from, and we'll do a real simple example in the next lecture that'll show you how to use them, but there's no real rocket science to it. I think it's pretty easy. And then the last thing we'll have to do before we move on to radiation is understand a little bit why they're behaving the way that they're behaving, right? So we can just use these blindly, just the same way that we could use convection correlation blindly, or any of the solutions blindly, and accept what they give us. But what makes maybe a better engineer is one who understands why, okay, what's going to happen as NTU gets really large, or what's going to happen as the capacitance ratio gets really small, or why are these solutions behaving the way that they are, right? Because that helps you, not only it helps you go one step beyond just implementing a solution to understanding what the solution is telling you, right? Which is really pretty important.